So, good morning, welcome back. So, we have come to the last two lectures of this section, namely the elliptic equations, and then after these two lectures you will be seeing other evolution equations. So, we are discussing about the eigenvalue problem yesterday. So, let me quickly recall that. Once we are discussing, let us do it. So, what we are discussing about this equation, minus Laplacian u equal to lambda u with in omega and u equal to 0 on d omega, okay. And the corresponding weak formulation is you have the corresponding weak formulation. So, let us not discuss about it. So, we are discussing about what are called solution operator. Solution operator starting with the f in L2, you solve this equation minus Laplacian u equal to f in omega, u equal to 0 on d omega. And so, you are looking for basically u in h1 naught of omega, and we associated a mapping G from L2 to h1 naught, which is contained in L2. So, you will get G from L2 to L2, where your Gf is the solution corresponding to f, that is denoted by u. So, basically this gives you integral of grade Gf. So, the Gf is the solution, grade V equal to integral of Fv for all V in h1 naught of omega, okay. And this we call it 1, and this is what we want to study, and this we call it 2. So, we will be using that. And what we have seen is that we have seen that G is self adjoint, symmetric adjoint, and what we have seen is that Gf G is a L2 inner product is equal to Fgg for all G in L2, that is symmetric. Self adjoint gives you that one, and then you also see that G is compact. And you have one more property, this is a second property. Third property, taking V equal to Gf in 2, because this is in h1 naught. So, you can take this one in 2, this will give you integral of f Gf is equal to integral of grade d Gf grade Gf, which is positive. So, greater than or equal to 0. So, putting together all this, G from L2 to L2 is a positive definite, it's a positive definite self adjoint compact operator. So, you see all nice things which you require, compact operator. So, apply spectral theorem of compact operators, spectral theorem for compact operators, you see. So, once you apply the spectral theorem for compact operators, what do you get? You get, so this implies what you will get, there exists an orthonormal basis, WM, orthonormal basis in L2 because you are doing everything in L2. Okay, orthonormal base is in L2 of omega, and sequence mu n, of course mu m are real, such that you get mu 1 greater than or equal to mu 2, like that. You have your mu m like that, which goes to 0. That is very interesting things, such that GWM, that is a solution corresponding to WM, is equal to mu m. So, it is the existence of eigenvalues for this, a discrete set of eigenvalues mu n, mu 1, mu 2, etc., which goes to 0, satisfying this equation. So, you see this is the eigenvalue for G. Now, what you do is that, so let me separate, you put lambda m is equal to 1 over mu m, that implies, if I take it, Wm equal to lambda m G of Wm, and by linearity you get that G of lambda m Wm. Okay. So, by this thing, anything G of f is the solution to a problem with f corresponding to f. So, this immediately implies from this relation Wm is the solution of 2. You just recall that 2, you see, that is how your GF is defined. GF is a solution corresponding to f. So, you are getting that Wm is the solution of 2 corresponding to lambda m Wm, you see. Therefore, so that is exactly meaning that is integral of gradient of Wm, that is a solution, gradient of V is equal to lambda m integral of Wm V. This is true for all V in H1 naught of omega. That is meaning Laplace, that is equivalently, that is in the strong form, Laplacian of Wm equal to lambda m V Wm. So, you have solved this eigenvalue problem, you are getting it. And Wm is an, or recall that Wm is an orthonormal basis in L2 of omega. Okay. And you also observe that since lambda m is 1 over n, 0 also you have immediately this, right, 0 less than lambda 1, less than or equal to lambda 2, less than or equal to etc. This goes to infinity. Okay. So, there is an immediate thing, yes, you get a Wm, it is a nice thing, Wm is in H1 naught of omega. Okay. We have this one, we have Wm is in H1 naught of omega, but you can apply regularity result to claim Wm is in C infinity of omega, and in fact if omega is smooth enough, if omega is smooth, then Wm is in C infinity of omega. You can go up to the boundary. How do you see this one? To this is a quick proof, that is not difficult to see that. Since you see Laplacian of Wm is equal to lambda m Wm, this is in L2. So, by regularity, this is what you are using it, regularity it gives you Wm, which is a solution, Laplacian of Wm, so it is in H2. So that will imply, so you iterate it, so now you have Laplacian of Wm is equal to again lambda m Wm, which is in H2 now. Okay. So that implies Wm is in H4. So you apply repeat it. So you repeat. Once you repeat it, you get Wm is in Hk for all k equal to 1, 2, 3, etc. Of course, you get H2, H4, etc. We are working in non-bounded domains, you will get it in all other H3. And that implies Wm is in C infinity. And you know this one, intersection of Hk is contained in C infinity by embedding. So you know that when k is large, you get some smoothness. So we have Hk is in every k, you get C infinity of omega. So you have this smoothness. Okay. So I want to do something more about these things, some interesting things. So I am going to introduce H1 of omega, which you already know, gives you define this norm, define the norm which you know already, define the inner product. Inner product for this present lecture, let me write it uv, the gradient inner product, which you know already, grade u, grade v, which is equivalent to the normal inner product, which is equivalent to H1 inner product. Okay, H1 inner product. H1 means grade u grade v plus integral of u. Okay. So going to take this thing. Okay. So what my claim, which I am going to do it again, claim lambda m power minus half Wm is an orthonormal basis for H1 naught, of course with that inner product. Okay, that is what we are going to. So you have to compute that. So let us compute. So recall 2, take V again in the weak formulation, take V equal to Wk. So let us see the proof. It is a very simple, nice, rather what we call it, cute proofs. So take Wk in the weak formulation. Weak formulation, we work with that weak formulation. So we will give you gradient of Wm, gradient of Wk. So Wk is the test function I am taking, is equal to lambda m, this is the corresponding eigenvalue Wm Wk. Now I multiply by lambda m power k. So I will take, that is what I want to see, this is a orthonormal basis, minus half Wm gradient of lambda k power minus half Wk. So with lambda m I have to multiply the right side also with lambda m power minus half lambda. So one of the lambda power m, one it will cancel, one half it will cancel, and you get lambda m power plus half lambda k power minus half into Wm Wk. But Wm is already orthonormal. Orthonormal basis for L2. So, this will be lambda m power k, lambda k power minus half into delta mk. But this is delta mk trivially, because when m not equal to k, this is left side is 0, right side is 0. When m equal to k, lambda m power half and lambda k power minus half will cancel and you get that one, and that is precisely you want to be orthonormal. So, that will give you is this sequence lambda m power minus half Wm is orthonormal in H1 naught with that norm. So, this you recall, this is the norm of lambda m power minus half Wm lambda k power minus half Wk in that norm, gradient norm. Okay. So, you have an orthonormal basis. So, now what is the second part? This is the first part. The second part, to see it is a basis, to see lambda m power minus half Wm is a basis. We use the kind of trick which you will again. So, this is what normally you do it, right. You interact, you have to prove that it has no other independent vector in that with respect to that inner product. So, choose V in H1 naught omega such that this norm V lambda power minus half Wm equal to 0 for all V for all m equal to 1 to etc. So, what you have to prove that, V equal to 0, that is all. Okay. So, with that you have to prove this V equal to 0. So, therefore, this gives you 0 equal to integral of grade, of course lambda m is a constant. So, I can take here minus half gradient of Wm, I can interchange, that is not a problem, gradient of V, but Wm is an eigenvector corresponding to lambda m. Okay. So, this will be lambda m power half integral of Wm of V. So, that implies this integral of Wm V, that is L2 norm, you see Wm V, this is the L2 inner product equal to 0 for all m 1 2 3, but Wm is a basis for L2, Wm is a basis for L2, basis for L2, that implies V equal to 0, because there is no eigenvector, there is no vector independent of Wm, V equal to 0. That is what you want to prove. So, it proves, you see, so you have your basis. All right. So, now with this interesting thing, we go to what are called the Rayleigh quotient characterization, and actually this is actually it can come from Rayleigh quotient characterization for lambda m. Of course, you can derive all these results from general compact operator theory can be derived from general thing, but you have your very specific G here. So let me do that job. Can be derived from the general theory, but it is nice to get familiarized few things, if not everything. So you define the Rayleigh quotient. What is this Rayleigh quotient? For V in H1 naught of 4, V in H1 naught of omega, V not equal to 0, not equal, define RV equal to this one, integral of grade U V grade V by integral of V square. That is nothing but your grade inner product basically by VV, your L2 inner product. Okay, L2 inner product. Okay. So clearly Wn is an eigenvector. So that is exactly that one. So since Wm is an eigenvector, for lambda m implies Rwm lambda m. Okay. I want to tell you something more, something interesting here. So you see, you have Wk, recall that orthonormal basis for L2 and lambda k power minus half Wk orthonormal basis for H1 naught. So I can look for Fourier expansion, Fourier expansion. So what is the meaning of looking for Fourier expansion? You write for any V in L2 as V equal to sigma alpha k Wk, where your alpha k is equal to, you take that inner product, integral of V Wk. So you are taking inner product V with respect to Wk. That is what you do it, right? That is nothing but sigma V Wk with L2 inner product. It's not enough space there, so I will do it. Now Fourier expansion with respect to lambda k power minus half Wk. So that way, so you write V equal to summation beta k. So you have to write the Fourier expansion with respect to that. So that is why you write here Wk. So that is the way you have to write it. Where your beta k, you have to exactly is in H1 naught. You are looking for in H1 naught. Okay. So you will be looking your beta k is equal to action of V with respect to lambda k power minus half Wk with respect to the gradient. So that's same as lambda k power minus half integral of grade V grade Wk. So you see now Wk is an Wk is an eigenvector. So this is nothing but lambda k power minus half, and this will be lambda k Wk. So lambda k V Wk. So you see, because it is an eigenvector. So that's the equation you get it. So you get it lambda k power half Vwk is nothing but your alpha k. You just see that. So your alpha k is your Vwk with respect to the L2 now. So you substitute there. Therefore, V is equal to lambda k power half alpha k lambda k power minus half Wk. This is an interesting summation. Same alpha k and Wk. So the Fourier expansion, so same Fourier expansion you are getting. So the Fourier expansion is the same in both spaces. Fourier conclusion is a nice observation. The Fourier expansion is the same. The Fourier expansion is the same in both spaces. Expansion is the same, even though the expanding things are for different L2 and H1 naught, and which of course implies you can get an approximation. So if I define the VL, now I can take the same expansion. If I take k equal to 1 to L, alpha k Wk will converges to V sigma alpha k Wk in L2 as well as and in H1 naught, same space. That's an interesting observation. Okay. Now let me at least do one thing and then continue in the next class. So at least one more step I will do. So now look at RVL. RVL, the Rayleigh quotient corresponding to VL is equal to, so you can just write down sigma alpha k square gradient of Wk. That is what you just write down the definition. You just recall into sigma alpha k square, and but this is a eigenvector. Wk is an eigenvector. So this is nothing but sigma alpha k square lambda k Wk lambda k. So we normalize it always. It's an orthonormal basis. So we normalize with respect to L2. So this is nothing but your lambda k Wk which is 1. Okay. Integral, because it's an orthonormal basis, to 1 by sigma alpha k square. So this so lambda 1 is the least eigenvalue. So this is greater than or equal to lambda 1. Okay. So RVL is so passing to the limit, you get RV is greater than or equal to lambda 1. That implies the minimum RV V in H1 naught E naught equal to 0 is greater than or equal to alpha 1 lambda 1. but then infimum you can call it. Infimum but infimum is achieved, but inf is achieved at RW1 equal to lambda 1. So, this implies lambda 1 equal to, so maybe I will write anyway to continue. So, that implies this inequality. So, that implies the first characterization, the lambda 1 is equal to minimum of, so you can minimize your Rayleigh quotient. So, so lambda 1 is achieved at the minimum of that. Okay, V H1 naught V not equal to. Okay, so I will I have little more, probably I will start with in the next class. Okay. So, we characterize now in the next class, we characterize, I will not do all the details and then prove one more thing, characterize lambda m. Okay. So, we will stop here and continue with the characterization of the higher values by a minimax principle. We will give these formulas which you can also little bit work out, but it is not. But you also look into the general compact operator theory. Thank you very much.